Good afternoon, ladies and gentlemen. So I've got the task of sort of putting the wrapper around all of this, and sitting in the audience, I was conjuring up a vision of sort of alien exploration from space, coming down with from satellite imagery, and then coming down, sort of scanning the Earth from low-flying aircraft, and then down to the Earth sampling on the ground. Then we're down into 2D and 3D seismic, and then there's obviously other considerations too, which is the response from Mother Earth herself, which is passive seismic, which is something that I'll talk about. So there's an overview of the presentation, and the presentation will be centered around our exploration activities and appraisal in Uganda. So, as I say, I'll start with the regional geology and finish up with considerations for 3D and passive seismic and the way forward for us. Okay, I think a number of you may have attended earlier talks at this venue on Uganda. Uganda is a landlocked country. It's a rift play. The Uganda itself, our activities are focused around the western arm of the East African Rift, and principally around the area of Lake Albert. The block outlines are given there on your right-hand side. There are 3 blocks, EA 1, 2 and 3, 3A. The permit boundaries run roughly up, halfway up the lake, and the other side is DRC Congo. And the earliest activities were in the southern part, because that's what we thought was the deepest play at that time. So there's an overview, and David opened with the sort of what are the key elements for exploration. We've got a good source rock, we've got a good structure, we've got we've got basement, we've got a good sedimentary pile. We've got good AVO indicators, which is also very helpful, good quality reservoirs. And also we have seeps, abundance of seeps in this area, and they've been known to exist since the early 1920s. So the early exploration activity for Tullow and its partners Heritage at that time were down here in the south of the basin. It started here and worked progressively northwards. I suppose there's a cautionary tale in the actual exploration history, in that bringing into play the geochemistry and the satellite imaging, the importance of satellite imagery in understanding the regional geology, because down in this particular area here, there are a number of seeps, and the first well was drilled here in Tarako back around the turn of the millennium, and that one, in fact, found some gas, but also found some CO2 at deeper levels. So it's a different type of geochemical sampling that was spoken about in the earlier talks, but this CO2 was later known to have come from a carbonate complex down here, so it was sourced at about 80 to 100 kilometers. But it contaminated the reservoir, and so this was not, this particular well was not viable as a consequence. And subsequently, then we did a sort of a geochemical survey of the lake and the land area down here, fairly extensive surveying, and could identify the corona of effect of this CO2 compartment. Then subsequent exploration activity was then focused on further north, getting away from that area, and then further north to Kingfisher and beyond, and up to the shallower plays up to the north here. Okay, so looking at the various plays in Lake Albert, we have got this is a satellite image of the Butiaba area. This is sort of about halfway up the Lake Albert. Out here you've got a sort of a shallow play with the sediment fed from the escarpment here, and this is a cartoon of it. And then out here you've got a major fault down into the escarpment. Here, deeper play in the lake, and most of our discussion this morning will be about, or this afternoon will be about the shallower play here. So this is moving up to the northern area, the northern part of the lake, and there are, as I said, the plays are predominantly shallow. They're all shallow, between 500 and 1,200 metres. And I suppose that's the key thing, is to devise an exploration strategy that would best optimise our return, for this shallow play environment. And bearing in mind that we had started in the southern part of the lake, the time was ticking, and we needed to use technologies that would give us probably the best value for money going forward. And this is a basin opening timeline for these areas. You can see we started down in Block 3A in 2001, working our way up. And I suppose the breakthrough would be discovery of oil in the middle part of the basin in around 2005, 2006. And I suppose around that time then we diverted our attentions up to the northern part of the shallow play area, and we realised that it would take some time to acquire large-scale seismic, so we were looking at other complementary technologies, and it was this time that we considered modelling the FTG that was spoken about by David earlier on. And so I'm going to talk to you a bit about that. So just to give you some geographical sensing on where we are, this is the area to the south again. We moved up, we had some discoveries here, and then moved up to this Butiaba area, and this is the area that we did the FTG. And this is the area that we've had most success since that time. That's a blown-up version of the same area. So we did some modelling, and we did some modelling with a number of companies, and Archex certainly contributed to this. And I suppose it's a very good candidate for FTG, this is the Albertine Basin, because you've got significant offsets at the basement itself. So this is the basement. So where you've got these large offsets with an infill of the more recent sediment, you've got a significant density variation, as you'd expect. So you would expect that a gravity survey, and particularly a high-resolution gravity survey, would pick up these, and in fact it does. So that's quite important. But also you can see this is the difference between sort of normal gravity, what you'd expect a normal gravity survey to give, and this is the TZZ of a gradiometry survey, which David spoke about earlier on. And you can see that it's a much higher frequency. You get a lot more information from the shallower sediment pile, as it was stated earlier on in the earlier presentation. So that's was quite important. So before we embarked on the survey, we had a good picture of what we were going to get. And I would say in this case, for gravity gradiometry, it's pretty much what it says on the tin, because we've had some fairly spectacular results from this technology here. So this survey was flown with a very loose drape of only 80 metres above the surface. This is because the area was fairly flat, apart from the escarpment where we ran the lines parallel to the escarpment. So for gradiometry, you can fly it at different levels. It depends on the topography. This is probably this is a very low-lying survey at 80 metres. Typically, you'd go up to maybe 300 metres, but you get quite a good resolution. So most of the lines were shot in this direction, and then, as I said, along the escarpment, we shot them parallel to the escarpment and then merged them later on. Now, the whole thing about gravity gradiometry is that you can. This area is about 2,500 square kilometres. So it was flown in about three months, and there was quite a fast turnaround of the data. So you can get a pretty good quick look interpretation within a few months, whereas a 3D land survey in this type of environment, this is not a desert environment, takes some time. The productivity levels would be probably about a fifth or more of what Ian spoke about in the desert. Okay, so this is the area for the gravity survey. So it was collected between February and June 2009. It was quite important because we had a fairly intensive drilling campaign coming up, so we needed to get some information on the leads. So this is just a zoom in to compare the difference between ground gravity and gravity gradiometry. You had some examples from earlier on. This is the one from Uganda. This is just a test. We first did a test swath in this area called Kasimini to see if the technology would give us what we were looking for, and then and also to determine what line spacing to acquire to fly at. And we decided we would acquire the whole thing at a very dense line spacing of 150 meters. So this is a comparison of ground gravity and air gradiometry at 450 meters in the center, and our gravity gradiometry at 150 meters spacing, line spacing, on the right-hand side. And the white lines are some faults that we have put in. The star here is just for reference. It's an area for a Kasimini well in the area. And the ground gravity, this would have been acquired by a government agency earlier on. It was made available. It was in the public domain. We use this to actually focus the first phase of our 2D sparse seismic many years ago. And as David said earlier on, you can use it to actually identify the highs. But because of the sparsity of sampling, and these are the actual ground gravity stations, because of the sparsity of sampling, the whole thing, the gravity field was undersampled, and so you get effectively aliasing. If you fly at 450 meters, 80 meters above the ground, using FTG, you get a different picture emerging. And this picture is one of gravity highs, and these are the basement highs that I spoke about earlier on in the modeling. And you can see, even at that line spacing, that the offsets between the basement and the sedimentary pile were becoming evident. And if you go to the more dense sampling of 150 meters, then the whole thing becomes even clearer. And it's on the basis of this, we extrapolated this across the entire area of 2,500 square kilometers. And this allowed us then to high-grade areas where we could drill, because these basement highs were the sort of the locus of migration of the oil in the area. And so we very successfully then identified where these highs were, and then using the sparse seismic we did an integration. So these are just some images of the 2,500 square kilometers, and you can see, which I hope you can see the patterns that are emerging, but the gravity highs are the red areas, and you can see Kasimini well there for reference. And these are this is the gravity draped on the seismic contours. So these here are the seismic contours for the basement. And there was a very, very good, this is from the 2D seismic, sparse 2D seismic, very good correlation between the gravity and the seismic at basement level. So, we certainly felt we were onto a winner there, and further developed the work program, by reprocessing some of the seismic and then looking at various methodologies for integrating the seismic in time series versus gravity and density. Okay, and that's a sort of an angled image of sort of slanted angle, so to give you some idea of the relief and also the correlation with the faults. Okay, so coming to a model then, it's, putting all this together, or advancing the integration. You've got this, first of all, you've got, this can be gravity and magnetic. I'll put in magnetic there, but it was first developed as a gravity and seismic sort of integration process with in collaboration with Icon Science, which they termed Gravisize, but we also inverted the seismic to see what contribution that had. But the whole idea is then that you've got a gravity inversion, you've got a seismic inversion, and you've got this optimization loop. You've got to effectively reiterate the gravity inversions and the seismic inversions to see how they fit. And of course, both of them are based on modeling, so they're not absolutely correct. So you've got to adjust one or both as you go along. And then what we're trying to do is get certain properties, density properties, which will allow us then identify areas of different densities within the basin and then give us some indication of where the major sand fairways are. So effectively we're looking at using rock physics to give us the reservoir properties in 3D using a 3D FDG output and a 2D sparse seismic volume. And this is an image of the FDG again. This is the inversion at the basement surface. And what we're doing here is running through various inversions, running the seismic through the gravity to see what the best fit was at the various areas. And this here represents a matrix of best fit for different values of gravity and density and velocity also. So this here, oh, that's not mine. This here is a degree of the of fit between the gravity and the seismic, and you can see at basement level. The white area is an area of best fit, and then these areas up here are sort of anomalous areas. We felt were related to some reactivation at the escarpment. There could be the basement itself is Precambrian, so it's a different composition. There's different mafic constituents in the basement. So we're beginning to get areas where we couldn't resolve unambiguously from the gravity and seismic alone. And so these are solutions that came, for example, to simplify it from areas of higher density clusters and the blue ones of lower density clusters. So you could actually match areas within the data set which were giving sort of a higher or lower response. And then we looked at the density data from the wells, and you can see here that in the sedimentary pile, the recent sedimentary pile, the density is very well behaved as you go down. But once you go to the basement, you get this huge variation, which is representation of the variable composition of the basement throughout the basin. So you've got a very well behaved density variation in the overlying sediment in the reservoir, but down the basement it varies quite a bit. And so, you know, hence that remains to be one of the key ambiguous areas going forward. We also looked at some magnetic surveys that were run by the government for the purpose of mineral exploration some years ago, and we reprocessed that and compared the magnetic basement, depth to basement, deconvolution to that derived from the seismic 2D. And there was pretty good correspondence. So this is another data set that can be used, another layer with the gravity and the seismic, and you can do a joint inversion to further de-risk the contribution from the basement. And this is what we come up with. This is the kind of picture that's emerging. On the right-hand side is a seismic profile of the Casamini area. And you can see this, the fault offsets, and you can see the offsets of the basement. So that's what's really been picked up by the FTG, and you can follow that along strike, even in areas where you don't have seismic, which is good. And then we try to generate this sort of an integrated density property. So we're trying to identify areas where we've got higher density or lower density pods, if you like, this being a sort of a fluvial lacustrine environment, or sweet spots for future drilling. And this is what it sort of, when you integrate the two together, there's a picture of a representative 2D seismic grid going down over this area. And you can see these lineaments here, and these are areas where you've got sort of, are measuring the rate of change of the FTG response. And they correspond to the basement faults that I spoke about earlier on. So you can actually correlate between sparse 2D lines using this type of display. And then sort of the holy grail then, well, we're still working on that of course, but is this sort of density distribution throughout the reservoir. So it's been a very useful exercise. And on the back of that, we continued our drilling program, and we've drilled 38 wells in the area, and only one of them has failed to sample hydrocarbons. And interestingly enough, this is the Awaka one in 2009. I suppose if we've had the FDG at that time, that was pre-FDG, we would have known that that was in a gravity low. So I think it's proof of concept. And here's an image that will support that statement. This here is the Awaka well, it's right on here. All around here you've got green wells that were drilled on these gravity highs. They were all successful, but this one here, albeit encountered a good reservoir, good sand, but it was in a low. So I think that's probably the strongest sort of support I could give to FDG. It certainly worked in this area. So at that point, I think it was it's useful to point out that it was crucial for us to have this technology to push ahead our exploration program at this time, because we've been drilling on the back of this sparse 2D and FDG since, and we've had that such success, 37 out of 38 wells. And of course that gave us time then, it certainly allowed us to build up the volumes, which was hugely important, because that then would determine what our future plans would be going forward. And of course, the future plan then has to be to come in with some 3D seismic, and that's what's planned, and I'm just going to talk about that for the remainder of the talk. So it's different to the desert type of scenario that was described by Ian earlier on. This is a very highly environmentally sensitive area, and that's why it was very helpful for us to be able to acquire an airborne survey first, because it minimised the disturbance to the population. And now we've got to go back and sort of carefully find our way through the area with a 3D seismic survey. And we're starting in this Casamina area, and this survey is ongoing at the moment. But you have to bear in mind that this area over here is all populated by animals, national park. This area up here is very sensitive also. And indeed this area where we started, probably less so. But this is sort of the land utilisation, and we had to, because it's such a shallow play, we have to sample very carefully the near surface, because otherwise we would have too much noise in the stack and it would be undersampled, and we couldn't get the required fold at shallow levels, because these reservoirs are between sort of 400 and 1200 metres. We were looking at various other technologies we could employ, bearing in mind the environmental constraints. There's probably one of the biggest populations of crocodiles in East Africa, up in the Albert Nile, Victoria Nile. Lots of hippos, and lots of other animals in that place, in the national park, as I say, up there. So we have to be very careful. This is the type of vegetation, savanna type vegetation, we're prospecting through. So it's not an ISS type environment, so to speak. Most of the work so far has been, the data has been acquired using dynamite in explosives in drill holes. So we've been looking at these technologies that we were talking about earlier on. And there's a lot of emphasis in the industry at the moment on recording both low frequencies and high frequencies, low frequencies particularly for inversion purposes, so you get a much better inversion product if you can record low frequencies. High frequencies where you can get them, certainly. And also there's a lot of emphasis on low impact technologies, and particularly cable-less systems. And I can just go over where I think cable-less systems sit with us going forward. This is an example of one here. This one was presented. There's a presentation on this in Oil Voice last year. This is the Oyo system. This is the box here. There's a battery to go with it. This is their single phone, which we tried out, but we're probably more interested in multi-component at this stage. And you can get 3-component Oyo units. I'll talk a bit about that later on. But the key thing is that going forward is that we need to have flexibility to be able to acquire whatever data we need. And it's pretty much infill data on the back of an existing the existing 3D that's ongoing, because that's a conventional survey. The idea there being that, you know, with the shallow play, if you undersample in the shallowmost play, then you have the opportunity to go back and infill. And also, if there are if there's a lot of cultural noise at the time of recording, then you can possibly go back and record a patchwork under quieter conditions. So they're the kind of applications that we're talking about. So we had the opportunity to do a test, a seismic test a couple of years ago. We brought in a technology that was used many, many years ago, but has improved since that time. That's weight drop, and specifically accelerated weight drop. And the idea there was to be able to infill in the areas where you couldn't record with dynamite. Now, up to relatively recently, there were lots of issues, environmental issues in the industry, which would preclude the recording of dynamite shots close to habitations and close to graveyards and areas that are sensitive. And a lot of these were recorded in the literature as safe shooting distances, and for dynamite in fairly shallow holes, they often went up to 150 or 200 meters. So when you're in an area of very shallow play, if you cannot acquire data within 200 meters of a habitation or graveyard or road or whatever, then you're going to end up with huge gaps in the data, and you wonder whether it's worthwhile at all to record it. So we were looking at this and we said, well, let's look at another technology which will allow us to get much closer to these. And the solution we came up with was accelerated weight drop. We could have gone with vibrators, but this area, the ground is quite soft, and most vibrators these days would actually sink in this terrain in many years. So we looked at very light weight drops. We did some tests going forward along 2D lines, and we did a sort of a data quality analysis of what weight drop would give us versus the earlier required dynamite lines. And so we found the areas that closer to the river, the lake rather, were the areas that we got the best data, and then there was areas where it was sort of mixed and matched, and then there was areas in the most deepest weathering where the dynamite was preferred. But what we did prove is it was a sort of a complementary source, both impulse response. And this is the type of thing I was talking about. If you were to apply the sort of safe shooting distances that existed in the industry up to 2 years ago, and since that time the IAGC, with collaboration of a number of companies, have actually changed the specification whereby you can actually determine this using peak particle velocity measurements in the area, which puts us in a stronger position in that you can actually go out and do some tests and look at the ground response relative to that for that particular area. So these are the emissions I was talking about earlier on if we had gone with dynamite here. So we did a patch 3D weight drop survey. I'll show you some of the results of that. Oops. First of all, this is a 2D line where you've got, they're joined there in the middle. And this is an example where you've got using weight drop, high resolution weight drop versus dynamite. And you can see that the response in this instance is probably better on the weight drop side compared to the dynamite. They certainly match very well. These are two different lines. So it was quite a nice infill source going forward. Also, it is faster, like vibrosize in the desert. This weight drop can acquire data probably twice as fast as dynamite. That's even after the holes have been drilled. But again, you'd need some open terrain. So this is a comparison of, we'd say, 2D and 3D. This is sort of a 3D patch survey that we did. This is the satellite image, and this is looking down the cross line and inline of the 3D, and this is merging into the intersecting 2D lines. And this is the issue that we had previously, where, you know, with dynamite, we had all these villages popping up all over the place. Even since we've been working in the basin, people have been migrating in and taking advantage of the infrastructure that we put in place, and so this is becoming an issue going forward, which we feel we have adequately addressed here with this low impact infill source. So you can see the data is quite good from both. One interesting thing that came out of all of this, and I said that there's a lot of emphasis in the industry on trying to get low frequency data for inversion, was that because the AWD, or the weight drop, was at the surface, and the dynamite was in a hole below the surface, there was a different frequency response, or stack response from both. And this is an example of the accelerated weight drop and a dynamite stack. And if you look at the spectrum, and this is the AWD spectrum superimposed on the dynamite, you can see that we were actually acquiring lower frequencies using the surface source compared to the dynamite. And that's probably due to some ghosting on the surface, on the dynamite shot. So we were actually acquiring lower frequency data, which was definitely a bonus going forward. And if you look at the spectra of the shots, you can see that this is the case, that in the 0 to 10 hertz area for AWD, we're getting some good reflectors, whereas in the dynamite, it's virtually absent. And consequently then, or conversely rather, at the higher frequencies in the dynamite, we're getting higher frequency data where it's not that well developed in the weight drop. So the frequency band has effectively shifted using the two sources. So you can use these in a complementary fashion so that you can get the best of both worlds. And then there's always the issues of the near surface effects, statics. We did some modelling on where we were actually getting higher levels of higher numbers for statics. Certainly here near the lake, the static values were low, which because the water table was near the surface. Then as you move inland, we get a higher statics and higher and quality difference. So source selection is important for this area. And equally, if you look at shot records, and this is putting it through sort of filtering, adaptive filtering, you can see that the ground roll response in different parts of the basin are different, so you have to apply a different adaptive filter depending on the ground's circumstances. So it's not as straightforward as it may look, but it can be done. Equally, there's been a lot of development, and Ian was talking about the number of channels that have increased, but certainly in the processing world, the higher compute capability has delivered a lot of upside in recent years, and particularly in this case in interpolation. And this is a 5D interpolation. We've got sort of cross-line, in-line, angle and azimuth, and the fifth one would be time of frequency, depending on what domain you're in. But you can see that this is without the interpolation, and this is with the interpolation. So in a shallow play environment, you can actually get better coherence through these simultaneous interpolation algorithms or routines. So that's another upside to it. So coming back then to so the Empire strikes back, or the Mother Earth striking back at the other methodologies, we decided we'd have a look at what, it being a rift basin, have a look at what the actual, how much free seismic we could get, or free source seismic, or open source seismic, whatever you want to call it. This is passive. We wanted to record, there are many events in the Albertine group, on Albertine basin on a daily basis. So we had, we set out some experiments to record what kind of response we were getting. And we deploy two types of instrumentation. These are the ones that you would normally deploy for earthquake monitoring, and these measure frequencies from, I think, less than 0.3 of a hertz up to and upwards. These ones here are seismometer. They're used for earthquake study or earthquake engineering studies, and they record from 2 hertz up. So what we're trying to do is record data in the lower frequency band for inversion purposes. We're trying to record earthquakes to see what kind of information we're getting. We're trying to record multi-component, 3 components. This is a triaxial component geophone, so it measures 3 components, a vertical and 2 horizontal components. We're trying to get more information about the passage of P and S waves through the reservoir. So this is why you talked about earlier on how do you select what kind of wireless source you're going to deploy. Well, it depends what you need. For us, the battery life was important. These things can record up to a month. So if you're recording in passive seismic in the area, we can leave them out in the area for up to a month and record 30 days of passive seismic and come back and process that. You can also use them for 3-component active seismic recording. So if you want to go out and do a short seismic line, we can reduce the sampling rate, reduce the sample time, and record something that's more conventional in 3-component. So there's a variety of uses here. And there's a nice comparison in a paper in First Break of this month about MEMS, which Ian was talking about in the last talk. And MEMS, digital 3-component seismic recorders, or geophones, digital geophones, and compared to arrays and to these triaxial phones. So if you want to know more about that, it would be a good place to start. So we did an experiment then in the Butiaba area, and basically we put out these passive seismic recorders and left them out there for weeks. And the purpose of this exercise was to, well, we were trying to establish whether there was a tremor from the reservoir, a microtremor from the reservoir, from passive that could be identified using passive seismic techniques. And this is something similar to the active methodology that was proposed by Biology, which I spoke at an earlier session in this forum. But basically, we're using passive techniques, and we found that there wasn't, in fact, a discernible tremor response. But what we did find is that there was, depending on the sediment pile above the basement, we were getting a different passive response, and we could correlate that with the thickness of the sediment pile down to basement, which was exactly what we were looking for to further develop our integrated process using FTG. So that was quite a bonus. And it works something like this. I mean, basically, you've got an earthquake, you've got your passive seismometers sitting up here, you've got our between 400 and 1,200 metres, maybe 1,500 metres of sedimentary pile sitting on the Precambrian basement. And somewhere down here you've got an event, an earthquake, and basically the response moves back up, and once it hits the basement you get a splitting into the shear wave and the P wave, and the P wave then becomes a precursor to the S wave because it's moving faster. And that's what you're seeing here. So you're seeing outside the basement you're getting very little response because there's no sedimentary pile, but once you get back into the basement you get this long precursor. And it's effectively measuring P and S response. So we can use that going forward. And it also tells us that we're getting a good 3-component response in the area, which bodes well for future exploration. And this is just to give sort of further support to that statement, in that we've used different techniques for measuring velocities in the basement, both active, passive, using surface waves, using body waves from very, very low frequencies. And the one thing we can discern where the major velocity breaks are. There's a major one there, we'll say at 300 meters. And using all of these different techniques, we can come up with the same response. So there's a lot of confidence and a lot of redundancy in the actual data going forward, which is quite good. So one thing we didn't really talk about during the earlier presentations was the use of 3-component data in the industry today, and it's been around for a long, long time. And it all depends, I suppose, on the development of and the trust in wireless recording, and also single source and single sensor recording going forward. But here's an example of a test we did in Uganda. This is sort of a 2D profile using normal linear geophones, 12 of them. And alongside that then we ran a 3 components using the engineering 2 Hertz multi-component, and this is the P-wave stack from that, and you can see that they're very comparable. And if anything, from an interpreter's perspective, it's probably more attractive from an inversion perspective, in that it's much richer in lower frequencies, and if you were to filter that back, you'd get something like this as an output. So that's very encouraging going forward. So just to sort of wrap up then, bringing all these technologies together, I suppose it's all about, first of all, applying the principles of surveying. The very basic principle is surveying from the whole to the part, which is, I think everybody would have got that picture this morning. Even if you start with satellite imagery from space, if you're looking at response, response from digital imagery, from multispectral absorption, whatever that is, and then sort of moving down then to sort of regional surveys. You're using airborne techniques or marine surveys at sea. Then moving down to ground sampling, going down to seismic sampling at surface, seismic sampling subsurface, and seismic sampling way below the surface. That's passive techniques. All of them have got a contribution. They all work to some extent. And if you can co-visualize them all and reduce them into sort of common layers, so to speak, then you get a much better output from all the input data sets. And that's kind of what we're trying to do. And just borrow this image from Berkeley at University of Delft. They work in 3 different nodes: geophysical acquisition, structural imaging, reservoir characterization, and the idea that there's feedback and feed forward. And this is the whole idea of getting everybody's head around the table and seeing what contribution they can make from a playmaking, from a geochemistry perspective, from a seismic acquisition, imaging, engineers from reservoir characterization. What are they actually looking for? What are they getting? How can it be improved as we go along? So I think that's the key sort of way to make sort of incremental improvements to our workflow going forward. And then occasionally you'll find a sort of, if you like, a radical improvement, which is, I think we achieved using FTG in Uganda. I think you'll agree with that. Certainly allowed us to progress our, what was an exploration drilling program at that time, successfully, without having to wait. It wasn't so much the expense of 3D seismic, having to wait to acquire it was more of an issue. We got over that by that technology push and that technology contribution from a different source. So I think that's the message I'd like to deliver today. And I'll finish then with a slide, with a version, similar version to the one that David started off with this morning, that he borrowed from Angus, as I borrowed this from Angus as well. Angus McCost, that is. Basically, oil is found through teamwork and intelligence use of best technologies. And I suppose the key thing is that everybody needs to be well informed about what everybody else is doing and what their views are going forward. And that's something I believe we successfully bring to the table in Tullow. These various variable toolkits are out there. The SGR have been out. I remember SGR being used in 1985. The SGR2, that was a cableless system. That worked quite well. It was a blind system. These systems, it all depends on tailoring these toolkits to your specific requirements, whatever they are. But the key thing at the end of the day is that it's all about teamwork. So that's it. Thank you. I'd like to acknowledge the organisers. I'd also like to thank the sponsors and my colleagues at Tullow Oil and you, the audience. Thank you. Okay, any questions?
Or are you all desperate for lunch now? Yes, please. Well done. Thank you.
With the knowledge you've acquired, do you still have a competitive advantage, or have other people got the ability to use what you've done in a frontier district and leapfrog you in a sense?
I think it's pretty much horses for courses, really. You know, when you go to a different area, you've got to understand what the objectives are there. You know, if you can bring these technologies to other areas, but they'll work to some extent. Whether you can get the right blend of technologies to deliver, you know, the answers that you need is another thing. They're all out there, that's for sure. In terms of competitive advantage, well, people know what we're doing. And I think we're fairly open about that, and we share it with the community. These are technologies that are available, and it's just at the end of the day, I think it just comes down to teamwork and also the ability to take on risk, because a lot of this work we're doing ourselves in Uganda, we're actually doing it ourselves. We're taking the risk of bringing in this equipment to see if it works or not. It may not work, you know. And you know, Ian talked about getting budgets for seismic earlier on. We know that these seismic surveys work. These principles work. So if you seismic acquisition and marine seismic acquisition is an all-time high at the moment. So you know, these technologies are out there and available. You know, it's just a question of whether people are prepared to pay for them.
Yeah, please.
What do you think this has done to your success rate? Is it doubled your success rate, or obviously had very, very good success rates, but employment of these techniques, say, has it gone from 20% to 50%?
Well, I think it's been consistently in the 80s, 70s and 80s for the last three, 4 years overall within the company. You know, obviously in Uganda, we've been very successful. We've been very successful offshore Ghana as well, but also elsewhere. So, are you talking about the company as a whole, or just
this particular your whole space, Uganda?
Yeah, I think the focus is really to understand the play, you know, the various plays. Once once you understand what's actually going on there, then I think you certainly reduce your exposure to drilling very significantly. So obviously we've been far more successfully by taking that approach than waiting. A lot of these wells were drilled on seismic lines, and someone had to decide where they were going. There were about 4 or 5 phases of seismic lines based on integrated gravity and seismic going forward. So we had to judiciously decide where these lines were going to go, knowing that the wells were probably going to be sited on that. So I would say it's been key to our success going forward. But it's this backward and forward iteration that's absolutely key, and sharing collaboration.
Okay, anybody else? Is somebody waving? Oh, right, sorry, I didn't see you.
Your exploration's been on the eastern flank. To what extent is that determined by politics, and to what extent is it determined by geology?
It's been mainly on the western flank, the western rift, yeah.
Yeah, but the eastern side of the lake. You haven't looked on the western side, is that correct?
Oh yeah, I mean, well, I suppose there are a number of things there. It's tilted graben, so we know that a lot of oil is migrating up from under the lake, has to be migrating up from under the lake onshore. You know, we bought into the concessions in Uganda, so it's both sort of, I suppose, it's both politically fueled and also understanding the play. We understand that the oil is coming up, certainly in the shallow play, in abundance. And because we've got that acreage position in Uganda, that's where the focus of activities are. Indeed, there's been significantly less exploration across the other side of the lake, and we haven't been involved in that.
Okay, good. Oh, Keith? Yeah. You need to wave more, Keith. You know, it's sort of.
Sorry, one last very quick question. To what extent would you put down that the exceptional success rates achieved to exceptional geology rather than, as opposed to exceptional teamwork?
Oh.
Well, I suppose you've got to decide whether you're going to go into a basin in the first place. So I'd say that they're exceptional decisions. So to get at the exceptional geology, you need to have exceptional teamwork to make the decision to go in there. So.
Good answer. Okay, thank you, Joe.